Okay, so now we're kind of switching gears and moving into learning about probability. And this class will be the foundations of probability, and we'll kind of gear us up for the next few weeks of lectures on probability. On the DSC40A website, there are quite a number of good references that you can refer to for some additional practice problems. And probability is one of those things where the more varied ways that you hear explanations, the greater the likelihood is that one of them will click with you. And probability, some people just get it instantly, and it kind of makes sense to them. Some people it takes a little bit of work to get it. But these other resources are really great, especially the probability roadmap when it comes to solving problems that Janine made. So I would definitely reference those. So in the first few weeks, we really spent most of the time trying to understand this idea about empirical risk minimization. And by and large, what that means is finding parameters, and particularly the best parameters. And those best parameters will help us make good predictions. So that is the key takeaway from the last few weeks of DSC 40A. So this is and if this is in the summer that you're taking this with me, then this is of course will be the first 3 weeks of summer session, and this will be the final 2 weeks of summer session. But if this is the winter class that I'm doing, then of course this will be weeks 1 through 6 and 7 through 10. But we also, not in lecture, we won't go over clustering, but there may be some demos in class where we kind of walk through some ideas of clustering and how unsupervised versus supervised machine learning works. And particularly everything that we've done in class so far with this stuff has all been supervised machine learning, or with an eye towards supervised machine learning, because we have the Ys, our labels. With clustering, you don't have those Ys. And in the next last part of class, we'll be talking about combinatorics, conditional probability and independence, and working through the naive Bayes classifier, which the common problem that people do with which I'm sure we'll have a showcase of, is a spam filter. Okay. So what is the point of probability? And some of you may have taken like AP Stats or a high school statistics class, or perhaps you've taken some statistics university course. But really, probability is the entire bedrock from which statistics is really built on. The reason why statistics works is because there's this theory and the ideas of probability that come into play. It's a big cornerstone of statistics. And when we think about probability, we have data that we've been using these last few weeks to make predictions on. And specifically, we have data that we've been using as a mechanism to find those best parameters in our risk minimization. But what is like a data set, and how does that work? And well, a data set is essentially a sample of a population. So we may have a sample, and then we have this sample comes from this population, and that sample is our data set. And we can never have a data set that represents the entire population for all intents and purposes. And so this data set we're using to learn from the past to make future predictions. And so these are how this stuff kind of relates. And in order for us to know that our sample is good, And to understand what ability we have to make good predictions, understanding how probability theory works becomes very important, because probability deals with, in essence, predicting the likelihood of some future event. In this class, we'll use a lot of kind of toy examples like dominoes or cards or rolling dice or flipping coins. And those are good things to use to study because they have finite outcomes and they're easy to understand. And you can kind of see how the math works behind these kind of simple data generating processes. So, in essence, probability gives us this mathematical framework which allows us to quantify uncertainty, essentially. So we can predict the likelihood of outcomes, so to speak. And that's a really nice thing, because so far with statistics, you've really been used to maybe like collecting, analyzing, interpreting data, and focusing on maybe like making an inference about a population. But we can make these inferences, and we can know how to properly collect data and how to analyze it because of the ideas that probability gives us. So I've drawn this. If you've taken Cogs 9 with me, this figure is probably familiar to you. But we have here some data generating process, and this represents the real world. And in the real world, data is generated, whether that's us flipping coins, rolling die, or the example where we've been using in this class, trying to predict the commute time. The samples of commute time that we're collecting is a data generating process. And when we collect those, we get a sample. And a sample is just our data sets, right? So this is like our data set. And the data set is always going to be a subset of the population that creates this data. So for example, maybe to put it a little bit more concretely, like an example of probability would be you have a fair six-sided die. So you've got a fair D6, and you want to know the probability of or the likelihood of rolling a specific number. So maybe like, we'll write this as, given a fair six-sided die, what is the likelihood of rolling a 4? Right, so that's a question that we can answer with probability, because rolling a six-sided die is has a finite amount of outcomes. Right, there's 6 possibilities, and so we know the probability. We can calculate the probability of getting one of those, and that's given that it is a fair dice. That's an important concept as well. Oops, I'll start my pencil. So some statistics, an example of that would be like, suppose we have that same die, and we want to, I don't know, say, okay, well, let's write it down. Maybe given the same fair six-sided die, we roll it 100 times. Collect the data and analyze the distribution of outcomes. Right, so we'd have like some chart, and we'd expect there to be probably some uniform distribution of this outcome. But so these are the kind of things that statistics is trying to do. We're essentially analyzing the outcomes after they have occurred, and we've collected that data or observed it. And so these two things, statistics and probability, work hand in hand together. Probability is about theory and the prediction before some sort of event occurs, so before rolling that die. And statistics is about more like analyzing and interpreting data after we've collected these results. And both of these things, right, probability gives us a way of understanding the data generating process, which is why it goes this way, and statistics is a way of inferring or understanding or predicting or learning about that data generating process given some data set that we have. So this is how the two sides meet. And as you take more classes that include probability and statistics, how these two areas work together will become even more and more important and clear to you. So an example from this might be, we have all YouTube comments, for which there are many. And we collect YouTube comments. And without kind of getting into the details of how they're collected or whatnot, we say that all YouTube comments is a population, and a subset of YouTube comments is our data sets. And so we can use statistics to look at our data set and then make some sort of inferences about the population or to understand it better. We can also use probability to understand and try and calculate the possibility of getting certain types of comments or certain types of outcomes from this data generating process. So you kind of need both, because both these things go hand in hand, and they both can really help you. But it's important to remember always that this is a population, and this is always a subset, or this doesn't necessarily mean, though, that the data set is a good data set. You can have bad data sets that are not representative of the population. Of course, we see that all the time. So the plan is we'll introduce the key ideas of probability that will kind of help to set the stage, because at this point you've probably have understood some of the key ideas of statistics, especially from DSC10. And we'll introduce some of these key ideas of probability, and then we'll use that to study more about combinatorics, and then we'll go into conditional independence and talk about the naive Bayes classifier. So, okay, terminology is important, and probability has its own sort of vernacular that we'll want to learn about. And particularly, we have an idea about what an experiment is, what a set is, what a sample space is, and these all kind of work hand in hand, and what an event is. So an experiment, just like in the last two slides, rolling a die is an experiment. Flipping a coin, it's some sort of process whose outcome is random. And this could be, an experiment could be many different things, but we'll start by looking at very simple experiments in this class. For example, flipping a coin and rolling a die. And the reason why we do that is because it's easy to wrap your head around that entire thing to study it. So that's what an experiment is. A set is an unordered collection of items. And what is a collection, and what are the items? Well, these are deeper questions that you can ask, but the important thing is, how does a set work? And a set works exactly as you might think it works from Python, where it is a unordered collection of unique things. And in probability theory, sets are denoted with these curly brackets, and if you have two bars along a variable that denotes a set, that's talking about the number of elements in a set. So for example, we might say that we have a set A, and A includes maybe, I don't know, let's say 3 numbers. So this could just be 1, 2, and 5. And we would say that A equals 3. So that's the number of elements in set A. What those elements are, at this point we don't know, they're just numbers. Not terribly important, but it's just, that's how many elements are in set A. And a sample space, which typically is denoted with a capital S in probability, is the set of all possible outcomes of an experiment. And it can be finite or infinite. And we'll mostly work with finite in this class. So, for example, let's say flipping a coin. So S equals heads or tails. So in this case, S is a sample space, and it's all possible outcomes of an experiment. An experiment could be, for example, flipping a coin. And so a coin gives us a sample space, and our sample space is a set. And the set is made up of the outcomes of the experiment, either being heads or tails. And these are both unique outcomes. And we would say that the size of S equals 2. And this is our sample space. Same thing for rolling a die. This might be S equals 1, 2, 3, 4, 5, 6. Right? Maybe this is like a 6-sided die. And we would say that the length of S here is 6. These are all unique outcomes. Now, an event is just a subset of the sample space, and it is a set of the possible outcomes. And typically an event is what you're finding the probability of. So we might say that we have S equals, we'll do the same 6-sided die. And E is a subset. So we'll say S equals 6, and then 1, 3, 5. And so this would be the probability. An odd number. And so we would say the length of E equals 3. And this symbol right here is just the symbol for a subset. So E is a subset of S, which means E can only have items in it that occur in S. So we couldn't put like, a 0 in here. Can't do it. Can't put a 7 in here either. Can't do it. Let's talk about probability distributions. A probability distribution is a expression of the range of outcomes that could occur from, let's say, an experiment. And the probability of each outcome must be between 0 and 1, and the sum of the probabilities must also be exactly 1. So here are some good key things to think about. So this idea here of each outcome as a sample space S is important. And really one of the other key things, and probably the most important thing on this right here, is that it must be between 0 and 1. And that's each outcome. So, for example, flipping a fair coin, you have a 0.5 for heads and 0.5 for tails equals 1. And each of these outcomes for each of the probabilities for both these outcomes falls between 0 and 1. So, and the sum of the probabilities for each outcome must be exactly 1. So that's where this comes into play. And if you think about this a little bit more closely, the probability of an event is the sum of the probabilities of the outcomes in the event. So the event being E, this just says the total probability. Oops. And what this part is saying specifically is you add the probability of every outcome in the event E. So for each event in E, add the probabilities of the outcomes. So, and maybe a good, yeah, maybe we can actually put down like a little idea here. So let's assume we have, actually I'll do this black. Oops. So let's say that this is S and this is going to be rolling a 4-sided die. So for a 4-sided die, we have 4 possible outcomes. We have 1, 2, 3, and 4. And the probability of a 1 equals 1/4, and the probability of a 2 is 1/4. The probability of 3 equals 1/4, and surprise, surprise, probability of 4 equals 1/4. And so all of these add up to 1, and each outcome individually is between 0 and 1. So each of these individually are between 0 and 1, and the sum of the entire space is 1. Another way you can think about probability distributions is if you have like a neural network and you're trying to predict a handwritten digit. So let's say that somebody enters in something like this, and maybe it's not like the best drawn 3, so it's kind of like that. And then this image goes into some neural network, and then the output of the neural network is a 1/10 vector. We have 0, 1, 2, all the way to 9, and then we get a probability where it says this is 0, 0.0, 0.1, 0.1, and then maybe for 3 it was 0.7, and then for let's just say for 8 it was like 0.15. Well, I guess this would be like 0, 1, and 0, 5. Anyways, all of these would add up to 1, and individually they'd all be between 0 and this would be the probability of predicting 3, 1. So this is the output of the neural network is a probability distribution, and so you see these probability distributions everywhere. So it's just important to understand that it's the range of possible outcomes. So if you're trying to predict a handwritten digit, well, your range of outcomes is between 0 to 9, because those are the individual digits that you can predict. And rolling a 4-sided die, there's 4. Flipping a coin, there's 2. So that's the idea of a probability distribution. And there's 2 different ways to look at statistics and these probabilities. And one of them is called the frequentist approach. If you took AP stats, then you probably learned mostly a frequentist approach to doing statistics, which is purely based on observed data. So you'd have like a data set, and then you would make some inferences on it, and that would be a very frequentist way of doing things. So like up here, this would be our frequentist interpretation. I'll just write it right here. So this is like the and the kind of alternative way of looking at things is what's called a Bayesian interpretation. So this here would be oh my goodness. Bayesian. Okay, Bayesian interpretation. Where, with a Bayesian approach, we're really trying to use some sort of, or quantify some sort of prior belief, and then to update that belief based on observed data. So, for example, if the sun's going to rise tomorrow, a Bayesian interpretation to that might be, well, I'm very certain the sun's going to rise tomorrow, or rather, perhaps the Earth is going to turn on its axis, and the sun will come into view again. But I'm very certain that this event will happen because for my entire life and for all of human history, the sun has been rising, so to speak. So I have a very strong prior belief that I can use. And then tomorrow, if I observe, I mean, my prior belief is like 99.9999999 whatever percent certain that this will happen. And then tomorrow, I'm out there looking and the sun rises, and I'm like, okay, that justifies the prior belief that I had, and I can go ahead and update it. Where a frequentist approach to that might be to collect a bunch of data for, let's say, like the sun rising, and then look at the statistics of it and say, okay, based on some calculations, we can be pretty confident that the sun will rise again the following day, and that's what we're going to predict. And that's based off of looking at the statistics, the confidence intervals, so on and so forth. So this is a kind of frequentist approach to looking at things. They really care about observing data, collecting it, and using that without any prior belief. It's kind of like a dead set experimental approach to doing statistics or analysis. And intuitively, most people, especially people who haven't taken any statistics or probability classes, their idea of making predictions or inferences about real world events typically stems from a Bayesian point of view, because you have your own shared experiences in life and you use that when you make inferences or judgments. How well a sports team is going to do, or any sort of event that you're trying to infer out of. So those are we're with and to state that formally, Bayesian probability is looking at the likelihood of observing you have some new data given a prior belief of that outcome that you had. So that's the way to think about Bayes. And again, frequentists think just like long run frequency of events or a long experiment. In really at this approach to, or at this point in time, that regardless what your viewpoint is on either of these, the math doesn't really change. Later on, it can, though, as you get into more advanced classes. So let's try a quick example just to make sure we're all on the same page. Let's go ahead and try and understand the probability of rolling an even number on a six-sided die. So we have, and think back to this nomenclature right here, right? Like, what's our experiment? What is our set? What is our sample space? What is the event that we're looking for? So our sample space is finite because we have a die that we're rolling. So we can create our sample space right here. And in the sample space, we have several outcomes. We have a 1, a 2, a 3, 4, 5, and a 6. And we know that the probability of getting a 1 is equal to 1/6. And I'll just write the rest of these. So the event that we're trying to capture, E, is rolling an even number on a D6. So that's going to be 2, 4, and of course 6. So we really care about, and we can even, sometimes a good way to think about, whoops, these things is your sample space is some physical thing, and we can divide it up into outcomes. Pretend that these boxes are all evenly spaced. And we would say like, okay, so we care about this one and this one and this one. So intuitively, that's 1/2. So our intuitive gut check is the answer is 1/2. But how do we get to that? And we have to think back to this equation right here. So let's go ahead and formulate this, because for rolling a die, you can close your eyes and do it or imagine how that would work, or you can draw it out a picture as well. But making sure you understand that equation is good, because when we get to more complex questions, you'll want to have an idea of what's going on. So here, we could formally say it as the probability of E. And remember, E includes it is this, is equal to the sum of all the individual probabilities. And this S here just means an individual event, like, maybe just let me write this out. This S does not equal this little s right here. That S is the sample space. This little S right here, and this probability is just talking about each one of these. So maybe we'll just put like a little S just to make that clear. So we would have my blue. So this would be I need a little more room. This would be the probability of 2 plus the probability of rolling a 4 plus the probability of rolling a 6. And each of these is going to be essentially 1/6 plus 1/6 plus 1/6, which is what this is telling us to do. And so this is just going to be 3/6, which is our 1/2. So intuitively, we knew it was 1/2, but here we can apply this equation, and this works because, and maybe that's a good thing to, a good caveat to add here is that this works because, well, no, I won't do that just yet. I'll do it here. One thing to note about this is that the probability of rolling an even number on a 6-sided die is not just 1/2 overall, but a really important thing to note is this 1/6, 1/6, 1/6, and we see it here. Why is that important? Is because the likelihood of getting any one of these outcomes is the same between all of them, which means this is a fair-sided die. So we should probably say that of rolling an even on a 6-sided fair die. And again, we could run this experiment many times, and we could use statistics to infer upon the fairness of this die by looking at the distribution of outcomes. But we're looking at equally likely outcomes, then what we really care about is being able to apply this idea. And the only time that you'll really want to apply this is when there's equal outcomes. Put a big one so you make sure to remember. Don't use this if the outcomes are different, because this is straight. This straight quotient here works well for this when the probability of each one is the same. So what's an example of this that we can look at? Well, we can look at flipping a coin 3 times. Let's go ahead and think about this intuitively. So flipping a coin 3 times, we'll ask the question, what is the probability of getting 2 heads, exactly 2 heads, only 2 heads? So one way to think about this is we can have an outcome where we have 0 heads. We have an outcome where we have 1 head. An outcome where we have 2 heads. And an outcome where we have 3 heads. So the probability of getting exactly 2 heads then would be one fourth, 1/4, 1/4. So these all add up to 1. These are all between 0 and 1. They're a quarter. So we say that the probability of flipping a coin 3 times and getting exactly 2 heads is equal to 25%. Okay? Now, this is a very intuitive way to think about it because I have 4 possible outcomes. The problem with this way of thinking, though, is that it assumes that each of these outcomes are all likely to happen, and they're not. So we have to actually look at all the individual coin flips. So this is not the correct way to solve this problem. So it would not be a quarter. So instead, we have to think about, don't think so much about outcomes, think more about the experiment. Like, what are the things that are happening? Like, what's our sample space? And our sample space is made up of a world in which we have 3 heads. Actually, there's going to be a lot of commas. So let me redo this. Okay, where we have 3 heads, and there's one where we have 2 heads and a tail, and there's one where we have a head and 2 tails, and there's one where we have, let's see, what else can we do? We could have a head, tail, head. We could also have a tail, head, head, and we can have a tail, head, tail. So 1, 2, 3, so that's 6. We could also have a tail, tail, head, and the 8th one, 3 tails. And this is because these 4 are kind of a reflection of these 4. So we have 8 possible outcomes now instead of 4. We'll sneak one more in there. And the probability of getting exactly 2 heads, well, this is 3, so that's not good. This is 2 heads, exactly 2 heads. And remember, we're not talking about order right now, just overall. 1 head, this is 2 heads. 2 heads, 1 head, 1 head, 0 heads. So this seems to be that we have, and well, let me put down also that the probability of each one of these, S and the 8th as well. Actually, redo this. So, color. So here, E is exactly which is going to be the set of heads, heads, tails, heads, tails, heads, and tails, heads, heads. So in this case, equals 3, and s equals 8. So guess what we're doing? The p probability of this event happening now is equal to, I'm not giving myself any room, E over S, which is 3/8. Notice how we were able to use this because all of these events here are all the same. So the outcomes of E, outcomes of S, gives us this, which is our answer. Let's talk about a couple of rules that we'll need in order to solve basic probability problems, and that is the complement, addition, and multiplication rules. And these rules are built off of the 3 axioms of probability. And those axioms are kind of like the law that governs probability, and that all probability kind of stems from. And we'll talk a little bit about the axioms here and there, but for the most part, they're pretty easy, but I'll touch on them as we go through. So first, let's start with the complement rule. And the complement rule says, let A be an event with probability P of A, then the event A complement is the complement of the event A that contains all the outcomes in the sample space. So when we say a complement, there's a couple ways of writing it. It can be written like this with a bar over it, or it can be written with a little C above it like that. I think it tends to be a little more common to see the C, but we'll use both interchangeably in our class. So before we do anything, it's always best in probability to draw a pretty picture. So we'll go ahead and start with that. And I really recommend and like drawing these little probability spaces. So this is the probability space of S, and we know that the entire probability space of S must equal 1. And let's define an event A. And it's very common just to draw circles. So we'll say that this is A. And anything that happens in A is A, and everything else that happens outside of A is called A complement. Actually, let's do it in a different color. So that's A complement. And we could assume that this is something like the probability of A might be, rolling even number on a 6-sided die. So this would be rolling, and this is for one roll of a 6-sided die, rolling a 2, 4, or 6, and this would be the complement, which would be rolling a 1, 3, or 5. Another thing to note is that the size of the A bubble, like this thing, is of course not representative of the true probability. That would be more of like a half. We tend to draw events with circles. So if you're on an exam or a homework problem, you see a circle, don't think that this represents the true area visually. But in this case, the complement of A is the probability of rolling not an even number. So it'd be about a half. But how do we define this with our equation? We'll stick with blue. So this is the probability of A, yeah, that's fine, plus the probability of the complement of A equals 1, because our entire probability space has to be 1. And we can also say that the probability of A complement equals 1 minus the probability of A occurring. So that's the complement rule. For any given event, this is for anything, the probability of it raining tomorrow or not raining, the probability of me getting a parking ticket at UCSD tomorrow, quite high probably, because UCSD loves to ticket people. So yeah, that's the complement rule. It's the occurrence of an event plus whatever other outcomes there could be. And rolling a 2, 4, or 6 could also be described independently as well. It's about 1/6 probability for each of those things, but collectively they make up our space of A. Okay, so perhaps okay, so then just for one last recap, everything that occurs in the probability space of A has to either be A or A complement in this example. Okay, so that's the complement rule. Let's go over the addition rule now. So the addition rule talks about mutually exclusive events, and we say two events are mutually exclusive if they have no overlap. So what's the first thing that we do? We start by drawing another pretty picture. And we'll call this S, and we know that S equals 1. And here we have 1. I think we used green for the complement, so we'll use red for the mutually exclusive event. Okay, so here we have B, and in the purple we have A. And in this case, A and B share no overlap. They are mutually exclusive, which means that they are separate outcomes, and they cannot occur at the same time. So let's say we have a six-sided die again. So we'll say, and do it in blue. And we'll say that we have A, and A is going to be rolling a 1, 2, or 3, and then we have B, and B would be rolling a 6. So this should be getting a 6, and this should be getting a 1, 2, or 3. And for this event, they're mutually exclusive because you cannot roll a 1, 2, 3, and a 6. You can only roll one die once, and these two events can't occur. There's no overlap. So here we could say that A and B well, they have no let's say they have no outcomes that overlap. That means they're mutually exclusive. So we would also say then that if that's 1, 2, and 3, and that's 6, then 4 and 5 live elsewhere in the space because all these added up equals 1. So it's 1/6 for each. A has a 1/2 chance of occurring, and B has a 1/6 chance of occurring. Thus, the complement of A and B, which would be whatever else is at S, has a 2/6 chances of happening. And how we can describe things like that is by using notation like this, which we'll start using, specifically this symbol and the additional symbols that we'll see in the following slides. But what this symbol is, we'll do it in, so this symbol is a union. And if you take DSC 100 with me, we'll do some set stuff with databases. So this is important stuff to learn for future classes. But this big U is a union, and what union stands for in plain English is the word or. So it means or. Probability of A or B equals the probability of A plus the probability of B if A and B are mutually exclusive. So that's what that means. And we're talking about the union of sets of A and B, because remember, these are sets. This is the set of 1, 2, and 3 occurring. And this is the set of 6 occurring. And so these are mutually exclusive, and the probability of A union B here would be 4/6 because it's of this and this happening together, and not the 4 or the 5. Okay, and the next one is called the principle of inclusion-exclusion, which kind of builds off of the addition rule, because now we have this other new symbol here, which is the end symbol or intersection. So we'll learn about that. An intersection, and union kind of go hand in hand together. So we will start with, as usual, drawing another very nice picture. However, in this case, we will start with, what do we do, A and B? That was purple and red. Okay, let's go for it. So here we have, I don't want an egg. Eggs are good, but not probability. And okay, and we will say that this is probability of B, this is A, these are the two sets. And let's talk about if A and B are not mutually exclusive, that means that there is an overlap between these probability sets, right? So we have to be able to describe that overlap. So we'll start with the probability of A, and we'll use this symbol, equals the, we'll go in purple again, the probability of A plus probability of B minus the probability, let's do it in green, the probability of A intersection B. So the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B. So let's just write these up here. So again, union or and. So the probability of A happening is all of this. And the probability of B happening is all of this. Let's assume this is all, there's nothing else. This takes up our entire probability space. So what we've done here is we've captured the probability of A, which was all of this, and then we've captured the probability of B, which was all of this. The problem, though, is that we've double counted this area where they overlap. And so and because it was double counted, and we know that the probability space can't be more than 1, so let's just assume that the probability of A is 0.5 and the probability of B is 0.5. So we'll just say, like, this is 0.5 and this is 0.5. But because they're not mutually exclusive, there's some overlap, there's some opportunity for them to occur together. Their overlap has been counted. And so then if we do this, we're going to double count this area right here. And so that's the reason for the subtraction here, is where A intersects with B. The intersection is the overlap. So we subtract that. So maybe it wasn't a good idea to write 0.5 here, 0.5. If they were mutually exclusive, the probability of A being 0.5, the probability of B being 0.5 is fair. But since they're not mutually exclusive, they can occur at the same time. The probability of A plus the probability of B gives us something that's over 1. And we know that our probability space cannot be over 1, so we have to subtract the intersection from it, the end. So the probability of A or B, when they're not mutually exclusive, requires us to subtract that intersection. So that's where, I'll use purple, that's where this intersection happens. And then this is the double counted. Okay. So that's the principle of inclusion, exclusion, and this is the principle of inclusion and then exclusion. And that's one way to think about it too, is that we're including this extra space and then we must exclude it. The addition of both probability spaces, given that they are not mutually exclusive and can occur together, means that we must exclude the overlap. So go ahead and try and work on this. Each day when you get home from school, there is a 0.3 chance your mom is at home, a 0.4 chance your brother is at home, and a 0.25% chance or 0.25 chance that both your mom and brother are at home. When you get home from school today, what is the chance that neither your mom nor your brother is home? And think about it as you have kind of several outcomes here. Either one, your mom is home, but no brother. 2, your brother is home, no mom. 3, both of them are home. Or 4, neither of them are home. And we want to say that the space S includes both 1, 2, 3, and 4. And there's some overlap between some of these, like your brother and mom are both home, has some overlap with either your mom or your brother being home. So 3 has some overlap with 1 and 2. And 4 has some overlap with 2 and 1. So maybe that might be an interesting way to kind of think about it as well. But we'll work through it and see what we get. So you can pause the video now and try and work through it. Okay, so the correct answer is not this, nor this, nor this, but the correct answer is C. So how does that work exactly? Well, we always start, at least I always like to start with drawing a pretty picture, because thinking about the probability space is kind of it builds up a nice intuition for the problem you're trying to solve. So let's go ahead and do just that. So this is our probability space, and in it we have a few things that can happen. We have, use purple. So we have the probability of your mom being home, and we have the probability of your brother being home. Now, if we go back, we see that there's a 0.3 chance your mom, a 0.4 chance your brother's home, and 0.25 that both your mom and brother are home. Okay, so that both of them are home is 0.25, so we just put 0.25 here. And we know that there is a 0.3 chance that your mom is at home. So what's 0.3 minus 0.25? That's going to give us 0.05. And for your brother, it was 0.4. So 0.4 minus 0.25 gives us 0.15. You see how this works? The probability of them being home by themselves occurs in this part of the space and that part of the space respectively. And where they occur together, or they're at home together, occurs there. And we already know that whatever goes on in here, the complement of this entire thing must be 1 minus. So you can kind of maybe think of it as like 1 minus both of these Venn diagrams equals our answer, because that's where no one is home. And that's going to be, our answer is going to be this sort of, use blue. Everything that can occur, that's where this other space is. Okay, so that's one way to think about it. And if we had 0.25 plus 0.05 gives us 0.3 plus 0.15 equals 0.45. So we could just really quickly do this as 1 minus 0.45 gives us 0.55, which of course is our answer. So that's kind of like a visual way of thinking about it. But if we want to use the equations that we have, there's a way that we can also do that. We have the probability, let me do it purple. We have the probability of mom being home equals to 0.3. And we have the probability of brother being home equal to 0.4. Yes, 0.4. And the probability, let's do this in black, the probability of your mom, right? Remember, we have to use that right there. What is this? So that's the intersection between both of these events happening. And that becomes, because we're trying to describe this interspace between these two probabilities, is going to be 0.25, yeah, 0.25. So if we look back at our equation right here, we know that the probability your mom or, that's a union, brother being home is equal to the probability of mom plus the probability of brother minus the intersection of mom and brother. So that's going to be 0.3, 0.4, yep, 0.4 minus 0.25, which is just going to equal 0.45. And then we also have the other probability of being alone. Maybe I will put that in, that's kind of blue actually. So the probability of being alone is going to be 1 because our S always equals 1. Probability of being alone is 1 minus the probability of mom union brother, which is equal to 1 minus, because we already defined it, 0.45, which is going to equal 0.55. Now, this might be a little bit more of a cumbersome approach to solving it versus doing it through a chart. I will say, though, that drawing it can become less easy as things get more difficult, but it is still nice to have it as a visual way of thinking about your problem. It just oftentimes makes sense to think about breaking up your probability space. Like your probability space is 1 or 100 of something or 1,000 of something, but it's a unit of measurement of 1, and we can use that as a space to kind of divide up the probabilities that we're working with. In this case, the probability of your mom being home, your brother, or together. So that's how we solve that problem. And the next thing that we'll look at is the multiplication rule in independence, which was the final thing from the multiplication or the complement addition rule and multiplication rules. Okay, so the probability that events A and B both happen is what's known as a conditional probability. So we're saying the probability of A intersection B, so of like both of these things, maybe the probability of both your mom and your brother being home in this case, equals the probability of A occurring multiplied by the probability of A given B. So this is a conditional probability, which means that there's some condition here, that we have to have. So another way of thinking about this line right here is what we really say is given. So the probability of here B given A is, let me write this out, probability of B given A. So this is given, but you can also think of it as the probability of B knowing or assuming A. So that's just another way of thinking about how to read that. And of course, this is our symbol for AND, which is union. So the probability of B given A means that B happens given that A happens. And the way we can think about it is the probability of both your mother and brother being home is the probability of your mother being home given that your brother is home. And for a problem like this, you could switch them the B and A can switch because neither one of these things has to happen. Like you wouldn't care if your mom came home first or your brother came home first. It's not how to think about it. Your mother being home doesn't cause your brother to be home, and your brother being home doesn't cause your mother to be home. It's just that the union of both of these things happening is dependent upon one of them happening too. So you need one to happen for the other to happen. In this case, like it's not that your brother came home and then left, and then your mom came home and you came home, and you'd say that your brother was there. No, it's in order for there to be a union, one of them has to be home, but it doesn't matter which one in this case. So that's the conditional probability. And if the probability of B given A equals the probability of B, then we say A and B are independent. So, this is how we think about A happening when you have no information about the event B. For two independent events, this holds true. Where's my thing? Right here. If A and B are independent events, it doesn't really matter. There's no condition on one of them being true, like how we're talking about with your brother and mom. Like the union of both of these isn't conditioned on one being true before the other. They just both happen. However, conditional probability is very important because a lot of things that we're going to talk about, especially with more complicated probability problems, there will be conditions on certain events happening before other events can happen. And we want to keep track of those, especially when we talk about things like machine learning. So let me just put something here. So this is independent. A and B, oops. Okay, so let's go through some examples. We'll start pretty simple with rolling a six-sided die. So I want you to take note, the language in probability statements matter a lot. So the results of each die, and perhaps a good rule or a good thing to get used to is to highlight or underline keywords, especially when you're reading exam problems. So the result of each die roll are independent from one another. So we're talking about independent events, super important. Suppose we roll the die once, okay? We roll it once. What is the probability of seeing both 1 and A? So both 1 and A. All right, well, let's start with a pretty picture. So this is S. And the probability of it happening are, we have a 1, a 2, a 3, a 4, a 5, or a 6. Okay, so what is the probability of seeing both 1 and 2? Well, we know that each one is 1/6 an event, of probability of each one happening. So does that mean that we have probability of 1 equals 1/6, the probability of 2 equals 1/6, so 2/6? Yes, no? Well, this is incorrect. This actually has a probability of 0. Probability of 1 and 2 equals 0. Why? Because we're rolling the die once, and you can't have two outcomes from one roll. So this is not a trick question, but this is a way of making sure that you're reading the questions and understanding them. This has a 0% probability of occurring. It can never occur. If you were to roll the die twice, then we could calculate this. But, right, because you have a 2/6 chance of getting it correct for each event if you were rolling the die twice. But we're rolling it once. So the first roll, we do have a 2/6 chance of seeing a 1 or a 2. We can never see 1. We can't see the other one. And the question stipulates that we see and both of them. So this is why it's a 0. Okay, suppose you roll a die once. What is the probability of seeing it? And just to continue, rolling a die once. What is the probability of seeing it? 1 or 2. Okay, so now we're dealing with or. We can do or. let's start by drawing our pretty picture. This is S, and we have a 1, a 2, a 3, 4, 5, and 6. So we're going to roll a die once. What is the probability of seeing 1 or a 2? Okay. So of seeing a 1 or a 2. So the probability of 1 equals a sixth, and the probability of seeing a 2 by itself equals a sixth. So the probability of seeing a 1 or a 2 equals 1/6 plus 1/6 minus 0. And we'll talk about why there's a minus 0 there in a second. That's going to equal 2/6, which equals 1/3. So why that 0? Well, remember, we have or here, so we have to think back. So we have or, and we know that our equation is a probability of A plus a probability of B minus the intersection. And lucky for us, there is no intersection when it comes to this because 1 and 2 are independent events. So that's just a way to make sure that you understand what's going on. Okay, let's do some more examples. So next question is our example. Suppose we roll the die 3 times. I'll keep highlighting things. So we roll the die 3 times. What is the probability of never seeing a 1 in any of the rolls? Never seeing a 1 in any of the rolls. So there's two things here. One is that this question is asking about unconditioned probabilities, right? These are independent events where we're rolling a die, and we want to see for each of these trials if we are going to see a 1 in any of them. So perhaps we can start by thinking about the probability of never seeing a 1 with just rolling one die, because we know we're going to need to calculate that at some point. So for one trial, never seeing a 1 is just the probability of not a 1, which equals the probability space of 1 minus 5/6, because if you don't see a 1, that gives you 5 other options on a 6-sided die, which equals 1/6. So this becomes a nice thing to keep track of because that's the probability of not seeing a 1 on any roll of a die. So we have that. And then how do we actually set this up? Well, the question is really asking us the probability of never a 1, which is equal to the probability of the first event not having a 1, and the second event not having a 1, and the third event not having a 1. So that's really what we're trying to calculate. And the intuitive, well, I'll say this. There's a more complicated way of doing this, but because these are independent events, we don't need to do that. So the simple, straightforward way of doing this is the, maybe I'll write it, yeah, I'll write like this over here. So the probability of the first never equals a 1 times the probability of second never equaling 1 times the probability of third never equaling a 1. That gives us 5/6 times 5/6 multiplied by 5/6, which is going to be 5/6 to the third. Now, if these weren't independent, so this is that's the big one right there. I guess it kind of looks like my handwriting. So if they were not independent, then we would need to do something like the probability of the first not being a 1 times the probability of the second not being a 1, given that the first was not a 1, because there's some condition now, but they're independent events. So that the die that you roll on the first trial has no bearing on the die you roll in the second trial. So we don't have to care about that. Now, suppose you roll the die 3 times. What is the probability of seeing a 1 at least once? Well, this should be the probability of at least once seeing a 1, which is going to be 1, a probability space, minus the probability of never seeing a 1. Now this will be 1 minus the 1 minus 1/6 to the third, which is essentially what we have over here. And this is going to be 1 minus just 5/6 to the third. And this gives us kind of like a general form of 1 minus, well, just a different color. 1 minus 1 minus p to the n. Okay, let us continue. So suppose you roll a die n times. Suppose you roll a die n times. What is the probability of only seeing the numbers 1, 3, and 4? Okay. So intuitively, it's good to think of these things as separate events. So we have the probability of the, let's save some space, of the first coming from the set 1, 3, and 4, and the second coming from the set of 1, 3, and 4. And this continues because we have n number. And n coming from the set of 1, 3, and 4. That's the entire probability. Now, these are independent events. So we say that the probability, so maybe I'll put this here. I'll keep doing it in purple. Okay, so that's like saying the probability of the first given 1, 3, and 4 to the nth power. Now it's important for it not to be thought of, this is written horribly. It's important to know that it's not times n, right? Like we're not multiplying these things by the number. So we're not multiplying the independent probabilistic event by the number of total events that we have, but it's to the power. And the most important reason why is because if you multiply it, you can get a number that's greater than 1. And the second axiom of probability states that a sample space is always equal to 1, and it cannot be greater than 1. And so the sample space has to occur between 0 and 1. The first axiom probability says that any event A that you have, the probability of A is a non-negative number, and that has to occur within a space of 1. So these two axioms of probability kind of help to define some of the rules that we're playing with. So if we take this a step further, we know that 1, 3, and 4 is a 1/6. So this is just going to equal the probability of 1/6 plus 1/6 plus 1/6, and that's going to be to the nth power, and we're going to have 1/2 to the n. Okay. So suppose you roll the die 2 times. What is the probability that the 2 rolls are different? Okay. So we can start off with saying that, well, okay, there are oftentimes when working on probability problems, there are intuitive and nice like shortcuts that you could use. So this is why, again, it's really important to read what is the probability that the 2 rolls are different, and we have 2 die rolls one at a time. And we want to know the second roll is different. So the simplest interpretation is that we just don't care what the first roll is. It could be anything. The only thing we care about is that the second roll is not the same as the first roll. And whatever the first roll is, that takes up 1/6 of our probability. So we have 5/6 remaining, and the second roll has a 5/6 chance of not being the first one. So the probability that both are different, both rolls are different, is just 1 minus 1/6, which is 5/6, and we're done. Because we don't care what the first roll is; it could be anything, and we're just subtracting that first roll from the possible 6 that we have in the second roll. So that's the easiest way to do it. Another approach that you could use is to look at the entire probability space. In this case, it would be equal to, come on now, it would be equal to 6 times 6, which is 36, because we have 2 rolls and there's 6 rolls each. So the space equals, we can have a 1 and a 1, or we can have a 1 and a 2, or we can have a 1 and a 3, so on and so forth until we have a 6 and a 6. So this is our possible probability space, and we would come to the same conclusion that the probability of them being both the same is 6 over 36, which equals 1/6. And the probability that they're both different is going to be 1 minus that 1/6, which is 5/6. Then we get that 1/6 from there. Okay. So let's talk a little bit about conditional probability now. And conditional probability is without a doubt probably the most important topic that we'll talk about in probability, because it lays the foundation for most of the machine learning that you do that will include probability, and for the probability that we work with in the rest of this class. So conditional probability is a probability event that might change when we have additional information about the outcomes. So if we are given more info, so there might be like your S equals 1, and your probability space might include many things that can happen. But when you have new information or more information, you might be able to take out or reduce the outcomes in your probability space. And so perhaps a new event now is your entire probability space. For example, we'll wait till we go to an example. But a good way to think about it might be that there are a range of outcomes that could happen. For example, the probability of either failing or passing a test. And I tell you that could be, let's say, a 50-50. But if I say the probability of you passing or failing the test, however, given that you do not wake up in time for the test and missed it, well, now that probability is going to be no longer 50-50, but the event of you not passing the test is your entire probability space because you didn't take it. So that's now just 1. It's 100% certain that you'll fail the test because you didn't take it. So that's how we can kind of think about that. And that's why we have this probability of A in the quotient now. So we say that the probability of B given A, and A is the new information that we have, and this assumes that A is not 0. But given that A is the new information that we have, we now can construct this quotient where A becomes kind of our new S. So you might say that S equals A and A's complement and maybe some other stuff. Doesn't matter. But now with new information, you might say that A is the only thing that can happen. And so A becomes the new probability space. So like our new probability space is just A, and whatever could occur in A. A could be, can have many things that happen. It's like rolling a six-sided die. A could be 1, 2, 3, and 4. And A complement could be 5 and 6. But I tell you, given that A is a weighted die and it will never roll a 5 and a 6. Well, now this is our new probability space. And so the probability of A is going to be just the 1, 2, 3, and 4 now. So what's the probability of rolling a 1, 2, 3, and 4? A becomes your new space. So this is the definition of conditional probability. And this comes from the multiplication rule where we have the probability of A and B, or A intersection B, and that equals the probability of A times the probability of B given A. And this is now with the new conditional information that we have. This is derived. Okay, so let's consider these next question. We want to know, so suppose a family has 2 pets. Assume that it's equally likely that each pet is either a dog or a cat. So 50-50 chance that it's a dog or a cat. So there's 2 probability questions we want to ask. The probability that both pets are dogs given that the oldest is a dog, and the probability that both pets are dogs given that at least one of them is a dog. And we want to know, are both these probabilities equal or are they not equal? And intuitively, you might say that they are equal just by thinking about it briefly. But this is where the idea of conditional probability comes in, because these extra pieces of information here both change the probability space that we're working in. So by changing the probability space that we're working in, we change the outcomes. So we'll go ahead and solve both of these. And let's start by always drawing a pretty picture. So let's compute the probability that both pets are dogs, given that the oldest is a dog. So we start off with S, and our original sample space has 4 outcomes. Either you can have a dog and a cat, and here the dog is, so if you're on the, let's put this here, older, younger, that's the mapping for this. So you could have a dog or a cat. You could have a cat and a younger dog. You could have an older dog and a younger dog, and you could have an older cat and a younger cat. So this is our entire probability space. Now, the probability that the oldest is a dog is going to be 2/4, right, in our probability space. The probability that the oldest is a dog occurs in 2 of these cases, right? So here's probability 1, 2, 3, and 4, and a dog is older in 2 of those. So we could say that the probability that the oldest is a dog equals 2/4 or 1/2. And let's say that that's pretty. Yeah, we'll do it this way. Okay, so think about the probability. So let's start by highlighting this. Okay, so both pets are dogs, and that the oldest is a dog. So these are 2 pieces of information, and we can derive 2 probabilities from here. So that both pets are dogs. This is going to be our probability space of B, and that the oldest is a dog is going to be A. So both pets are dogs. That occurs right here. So this is B. And that the oldest is a dog. Well, that's going to be 2 cases, right? So we'll say that occurs. Maybe we'll highlight this green. So, and Okay. So you see how, and we'll call this A. So you see how A occurs over both of these events where the dog is the oldest. That's this case and this case because the dog is the oldest. B only occurs in here because that's where both pets are dogs. Maybe I'll just do that. So event B is 1/2 of A. That's an important thing to write down. So let's just pretend, because we want to think about this in a manner that is bringing us towards conditional probability. Our original space was S, which is all of this. But now we have this new probability space, A, which is this whole thing. And B is 1/2 of A. Because we're computing the probability that both pets are dogs, right? Which would intuitively be 1/4. Because we said before that it's equally likely each pet is a dog or a cat. So if we don't consider any of this stuff, that both pets are dogs only occurs here, that's 1/4. However, we have some new information given. This given is the key right here. Given that the oldest is a dog, so we already know that the oldest pet is a dog, and we know that the oldest pet being a dog only occurs in these two events, not these two. So we know that this no longer is the reality. We don't even need to consider this in our probability space. So our probability space just becomes this right here. So we can go ahead now and calculate that. So we say that the probability that the both are dogs, given that the oldest is a dog, now changes our probability space. So we can say the probability that both dogs and oldest is a dog over the probability of the oldest being a dog. And that's going to be 1/4 over 2/4 or 1/2, which equals 1/2. So the main thing to take away from this one is that, or 0.5. The key point here is that this bottom part here is kind of like our new probability space, oldest being a dog, because oldest being a dog, oldest being a dog is all we care about. So that's where this thing, the probability of A now, is our new space. Where before our space was all of this, now it's just this. So you can kind of maybe draw it out as, the new S is equal to this is B, this whole thing is A, and then this is dog, cat, and dog, dog. So we've kind of like, done that. Okay, so let's put that down. So this was 0.5. And now let's take a look at this, and let's compute the probability that both pets are dogs, given that at least one of them is a dog. Well, we've already drawn this picture once, but we'll draw it again real quick. And we had dog, cat. We had dog, cat. This was cat, cat. This was dog, dog. And this was cat, dog. Yep. Okay, so now we had, how did this look? This was like this, and then we had this, and we might as well do this too. Ooh, that is ugly. Okay, so we still have, this is still B, and this is still and this is still A. And the key things here are, now let's compute the probability that both pets are dogs, again, given that at least one of them is a dog. So before we had given that the oldest is a dog. But now, and this is going to be our A, and this will still be our B. So given that at least one of them is a dog, well, it looks like our probability space has grown now, because in this case here, at least one of them is a dog, not this one. So we can disregard this space, and we can add this to our probability space for A. And because the probability space in our denominator is increasing, we're going to get a smaller outcome because there's more possibility now, right? You can have three outcomes where before we only had two. So this part down here will increase, which will lower our probability. But let's go ahead and write it all out. So now B is not 1/2, but 1/3, because we added cat over dog, right? This was added to our probability space, our new probability space. So the probability of B given A equals the probability of A section B over probability of A. And if we plug that in, we now get 1/4 over 3/4. Instead of being 2/4, it's now 3/4 because we keyed it probability space, equaling 1/3. And notice, even though these lines are drawn kind of weird, that these represent fourths because these are all equally likely outcomes. This, and this. We've just removed this from our sample space because of this. It's telling us that this can't happen in our events. It's not a possible event that can occur. So this is 0.33. So these are not equal. Okay, well let's talk about dominoes next. So we'll start with the this domino example, and we'll finish it off. We'll finish it in the next lecture. This one's already going on pretty long, but just to kind of set things up, and consider a set of dominoes, for which case there are 28 total tiles. And just to make it pretty clear, we can have a domino that looks like this, and it's going to be functionally equivalent to this because you can just rotate. So these are the same exact thing. And you can also have a domino which has nothing on both sides. So this is going to be 0, 0. Or you can have a domino which has nothing and 1, so 0, 1. And domino can have up to 6. So you could have something that's like 1, 2, 3, 4, 5, 6, and 0. So these are all different types of dominoes you could have. So this will be our probability space that we're working from. And just to make it really quick, with the help of video magic, here are all of them laid out. Okay, and you can see here all the combinations where the tiles are the same. So like 0, 0, or if we had if this was 3 and 3. We don't need any of them in this triangle because they're just reflections of these. And we already said that this is equivalent to this. So having 0, 1 over here is the same exact thing as this one, so we don't need those. Okay, so we've got 28 total tiles, and as just a real quick warm-up and something to think about before you watch the next lecture, what is the probability of having a double tile? Well, we know that there are 28 total tiles, and we know that there are 1, 2, 3, 4, 5, 6, 7 possible double tiles. So 7, and that will give us 1/4. So that's how I calculate that probability. And we'll look at some examples in the next lecture that get a little more complicated. But we'll stop the lecture here today, or for this one. Here's a summary of all the things we spoke about in this lecture. And hopefully you can go through some more of these probability examples and practice them. It's not that they're like there's nothing computationally difficult. It's all about wrapping your head around the probability space and how the information you're given changes that probability space. That's the most important thing to understanding the use case, especially with conditional probability and how this denominator here changes things. All right, well, we'll see you in the next lecture.